welcome. Welcome to the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. And welcome to this, Perimeter's public lecture series presented by BMO Financial. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone here this evening. Both those of you here in the theater audience and those of you watching online on Perimeter's website or on one of our many science communication colleagues' websites around the globe. The lecture itself will last approximately 1 hour and will be followed by a question and answer session. Dr. Damien Pope and a team of researchers are behind their keyboards, ready to engage in conversation for the online audience and answer questions throughout the lecture and after the lecture. If you want to participate in that conversation, use hashtag #PILive. And also, if you want to have a question sent in for our guest speaker, send that in early so that it can be vetted through the process and make it all the way to my phone in time for Q&A. And now, it is my pleasure to introduce tonight's very special guest speaker, Dr. Amber Straughn. Dr. Straughn is an astrophysicist at NASA's Goddard Space Flight Center and is a member of the James Webb Space Telescope science team and the Associate Director of the Astrophysics Division at Goddard. She completed her PhD in physics at Arizona State University and has been involved in NASA programming since her undergrad, beginning with flying an experiment on NASA's microgravity KC-135 plane, also known as the Vomit Comet. She says she did not vomit. In addition to her research, Dr. Straughn's role with the James Webb Space Telescope science team involves, in addition to research, there's also lots of science communication. She is a highly sought after speaker who frequently gives talks at schools and astronomy clubs and museums and research societies. Dr. Straughn has appeared on the Discovery Channel, the Science Channel, PBS, Nova, National Geographic, BBC, the History Channel, Spike TV, and on Late Night with Jimmy Fallon and his Hubble Gotcha segment. Ladies and gentlemen, please join me in welcoming Dr. Amber Straughn and her talk, The New Era of Astronomy, NASA's James Webb Space Telescope.
Thank you so much. Thanks for that kind introduction. And thanks to the Perimeter Institute for being such a gracious host today. It's been so much fun talking to the researchers here and some of the students. And it really struck me today that we're so privileged as scientists working in communities like this to be able to work with creative, inspiring people who are doing things that they're so passionate about, things that they really love. And I feel like that's the same case for me at NASA. I have a job that I love, and I'm working with people who are doing really remarkable, incredible things. My passion for astronomy actually began a long time ago when I was a little kid. I grew up in rural Arkansas in the southern United States on a tiny farm. And as you might imagine, in a rural place like southern Arkansas, there's not a lot to do. But let me tell you something. The night sky was stunning. And so from the time I was a very young kid, I was interested in astronomy. I was looking up, and I was always asking my parents ridiculous questions that they couldn't quite answer. And I remember at one point, I asked my mom some out-of-this-world question. And she looked at me and she said, "I don't know the answer to that question." This was the days before the internet. And she said, "But you can figure it out." She said, "You're going to have to find out the answers to those questions." And that really set me on my path to becoming an astronomer. And I've ended up here at NASA, which is a job that I truly love. And so I'm really excited tonight to tell you about this amazing project that I get to work on, and to tell you a little bit about the history of astronomy at NASA. And of course, we can't talk about astronomy without first talking about the iconic Hubble Space Telescope. Over the past 27 years almost, Hubble has completely revolutionized our understanding of the universe in fundamental ways. And one of the things I love most about astronomy is that the questions that we try to answer in astronomy are so much more than science questions. They're questions that get to the heart of what it means to be human beings. These are questions that humans have asked and sought the answers to since we've been able to ask questions at all as a species. And Hubble has done amazing things to help us try to start to answer these questions. So the Hubble Space Telescope has been able to tell us about the universe on a large range of scales, starting from our cosmic backyard of the solar system, and then stepping out further in our own Milky Way galaxy to star-forming regions, so relatively nearby in a cosmic sense. And then, of course, the Hubble Space Telescope has also taught us not only about star formation, but it's taught us about stellar deaths. And of course, this is the process by which elements are spread throughout the universe. The iron in your blood was literally formed inside of a star. And I think that fact is so amazing, and it connects us to the universe. So these stellar deaths are often very dramatic and beautiful, and of course, we've also learned from Hubble about other galaxies outside of our Milky Way. And we've learned that galaxies not only exist out there, but they also sometimes interact. So part of my own research deals with interacting galaxies, and this is an example, a beautiful example of the antenna galaxies that interact. And when galaxies undergo this cosmic dance of interaction, really fun things happen. They form stars at higher rates. We think their black holes probably merge, and that's one of the things that cause black holes to grow over time. So Hubble has provided us all of this information about our solar system, about our Milky Way galaxy, and about other galaxies outside of our Milky Way. And then it's also, of course, taught us a lot about the evolution of the universe as a whole. Now, if I had to pick one single image of all of Hubble's amazing images as my favorite, it would be this one. So this is the Hubble Ultra Deep Field. I was very lucky. This image came out when I was in graduate school, so I got to do a lot of my dissertation research on this data. But in the Hubble Ultra Deep Field, Hubble stared at one tiny piece of sky for about 11 days. So that's like looking at the universe through a straw. If you imagine if you take a drinking straw and look up at the sky, it's this tiny little spot. You cover it up with your finger, your pinky. So in this tiny piece of sky, Hubble sees 10,000 galaxies. So every point of light there is a galaxy, a couple of stars scattered in there, but for the most part, they're all galaxies. And of course, these images are beautiful, but we also were able to learn remarkable amounts of things from these images. Just by looking at them, you can tell that galaxies come in a variety of shapes and sizes. You see in the foreground some common-looking galaxies, some spiral galaxies. But as we start to go deeper, we see that the universe changes as we look further back in time and further away in distance. And what we're able to do with these images and from spectra that we're able to take with these galaxies is learn about the chemical components of the stars. We're able to learn about these galaxies' black holes and how and if they change over time. And by looking at their distances, we're able to basically look back and track back into the early universe and figure out how, in a large scale, galaxies in the universe changed over time. And then, of course, at some point in these Hubble Deep images, we come to the edge. We come to what we can no longer see. And so that's, of course, the topic of most of my talk tonight, is what we're going to do to get beyond that edge. So that's a very brief, condensed history of the amazing 27 almost years that Hubble has been in space. And the Hubble Space Telescope, I think, is, in addition to being this remarkable scientific machine, it's this thing that we humans have built that have given us answers about these big questions of the universe. I think it's really important and it's really telling that Hubble has become an element of pop culture. You see Hubble images on the sides of U-Haul trucks and on album covers and in movies and on cartoons. Hubble images show up everywhere. You go anywhere in the industrialized world and you ask somebody to name a telescope, and they're probably going to say Hubble. And I think that really speaks to something deeper that these types of projects give to the world. I think that Hubble has become, again, not only an astronomer's tool, but it's become a resource for the world, a resource of inspiration. And it's really become something that we can be proud of as a species, of this thing that we've built that has taught us about the universe. And I don't really know exactly why. I don't know why people love Hubble so much. I'm glad that they do, but I'm not sure why. Of course, it's easy to be captivated and inspired by those beautiful images. But I'm not exactly sure why that is. I mean, they're beautiful, they're pretty, but why? You know, if you look at images of trees and of nature that we normally experience, it's easy to understand why we are captivated by those images. They're part of our experience. But nebulae aren't part of our daily experience. So it's really interesting. And again, I don't think I have the answers, but I think it might be connected to the fact that we, in some maybe subconscious level, some deep level, we know that we're connected to the universe. We know that when we look up at the universe, that in a sense we're sort of looking back at ourselves. We're looking back at our origins of where we came from. And I think that concept is very beautiful and it's universal. I think that the images that Hubble have given us, they transform and they go beyond national boundaries and language boundaries. There's something that is very deep about the reasons that Hubble has become this worldwide icon. So in that sense, you know, this is a world treasure, I think, that we have. And so, of course, what's next? What's after Hubble? What could possibly follow up the amazing science that Hubble has given us, the amazing thing that it is? And that, of course, is the James Webb Space Telescope that we're building now. And I truly believe that this telescope will be a worthy successor to Hubble. I think that in a lot of ways we've pushed Hubble to its limits, as awesome as it is. And we're literally building this telescope to answer those next biggest questions in astronomy that Hubble just can't quite get to. So I want to tell you a little bit tonight about some of the science goals of this mission and some of the ways that this mission is different than Hubble. So the first big key difference between Hubble and Webb is simply the size. So overall, Hubble's about the size of a school bus. Webb is more the size of a tennis court. Its sunshield's about the size of a tennis court, and it stands several stories tall. Now, the size of a telescope's mirror is very important because it allows us to, number one, collect more light, and number two, allows us to see finer detail in those images. And so this will by far be the biggest telescope that we've ever sent into space, by far. So this is a model of the James Webb Space Telescope. This was at Goddard. Unfortunately, I'm not in that picture. Very sad. But a lot of my colleagues are, and this is, of course, just a subset of all the people that have worked on this telescope over the past 2 decades now. So this is a model, steel and plastic, not the real thing, obviously, wouldn't be sitting outside at Goddard. But you can sort of get a sense of the scale of the telescope here. Again, that sun shield, about the size of a tennis court, stands several stories tall, huge telescope. And again, the reason for that is because it's completely driven by the science questions. The second big difference between Hubble and Webb is the place in space that Webb will be. Hubble orbits the Earth about 350 miles up. This, of course, is not to scale. But Webb will orbit the sun along with the Earth about 1 million miles out, about 1.5 million kilometers away from Earth. And it will follow the Earth in the orbit around the sun. And so this is a point in space called the second Lagrange point, L2. It is a semi-stable point in the whole overall gravitational system of the Earth and the sun. And it's a place where we can park spacecraft, and they sort of stay there, and they follow the Earth as it orbits the sun. That way we can always have easy access to communications with the telescope. And so that's where we're putting the James Webb Space Telescope. And the reason we're putting it there is so that it can get very, very cold. And that leads to the third big difference between Hubble and Webb, which is the type of light that Webb will see. So Hubble is primarily an optical telescope. It sees the universe primarily in visible light that your eyes see. It has a little bit of near-infrared capability, but it's primarily an optical telescope. Webb will be an infrared telescope. It will see the universe in red light, red visible light, all the way out to mid-infrared. For those of you that speak in microns, it'll be 0.6 to 28.5 microns. So near-infrared all the way out to mid-infrared. And again, this is completely driven by the science questions that we want to answer with the telescope. So why infrared? Well, this is the iconic pillars of creation, the Eagle Nebula, the iconic image from Hubble in optical light. So here is a fade into UV light. This was taken a few years ago, and then it's going to fade to near infrared, and you'll see the reason that we need infrared. With infrared light, you're able to peer through the dust and see the stars inside being born. So that's one of the reasons we need infrared. People often ask me if the Webb images will be beautiful like the Hubble images are. And I always point them to this. That's pretty beautiful, right? And that's a near-infrared image from Hubble. And so absolutely, we expect the Webb images to be stunningly beautiful. In addition to the amazing science we expect it to tell us. So those are the three big differences between Hubble and Webb: the size, the place in space, and the type of light that it will see. And so now I'm going to get to the science. What do we hope to learn with Webb? We have 4 main science themes, so 4 broad goals, things that we want to learn from Webb. So the first big goal is first light and reionization. So you remember that Hubble movie that zoomed through the Hubble Ultra Deep Field? We saw all those galaxies in the foreground, spiral galaxies, elliptical galaxies, and then you get to galaxies that have more strange shapes, and then you come to the edge. So when we look at these deep images from Hubble, the deepest galaxies, the most distant galaxies that we see are these teeny tiny red dots. And I encourage you, if you haven't looked at this image in detail, go download it in its full resolution and just scan around. You can spend hours doing it. But the most distant galaxies we've been able to see with Hubble are these teeny tiny red dots, just a few pixels. So we don't know a lot about them, but what we do know is that they're not the first galaxies. From what we've been able to tell from these distant galaxies, they exhibit properties that tell us that they're not pristine. They're not the first galaxies. And so what we want to be able to do is push beyond that limit and use Webb to see the very first epoch of galaxies that were born after the Big Bang. So we're talking about looking back in time over 13.5 billion years to see that first epoch of galaxies. Now, this is not easy, of course. That's why it hasn't been done yet. We have our theorist friends that build these beautiful models of the early universe. This is a simulation of the early universe that tells us what we think we should see in the early universe. So we expect to be able to see these young galaxies, these infant galaxies that turned on after the cosmic dark ages. But again, we've never been able to have technology that's allowed us to see back that far. So we've gone on the theories, and now we want to be able to learn more about what's going on there. So just some sort of fundamental questions in this realm. So what are those first galaxies? What are they like? And when did they form? Do they have black holes? We expect they almost certainly do. How do they cluster? And this whole process about reionization. So early on in the universe was mostly filled with hydrogen gas. And if a photon comes along, if light comes along, hits hydrogen, it gets absorbed, it can't get through. And so what we want to do is find that first epoch of galaxies that were able to shine enough light to sort of blow bubbles in the surrounding neutral hydrogen so that we can see through to see those first galaxies. So how did that happen? We know it was probably sort of clumpy. It happened in different places. And we want to know what the history of that was up until what we think we've seen as the end, sort of the end of reionization. And so what caused it? Stars, black holes, how did all of that happen? So there's a lot of open questions about what those first sources were and how they affected the surrounding universe. So this is a timeline. Many of you have probably seen something similar of the history of the universe in a chart, right? And so we have the Big Bang over here, and then present day over here. And so again, with Hubble, we've been able to push back and start to see, again, what we think is sort of the end of reionization. But what we really want to do is to see those first things that started blowing out those bubbles and started to shine through to see the first galaxies after they emerged from the cosmic dark ages. It's one of the primary goals of JWST, and it was one of the drivers. It was one of the reasons that we started to build this telescope. So the second big science theme for Webb is galaxy assembly. And this is one that's very near and dear to my heart because this is my area of research. So we want to learn more about the process, the very basic process of how galaxies build up over time. So the Hubble sequence is the name we give to the nearby galaxies that are spiral galaxies, elliptical galaxies, balls of gas, or irregular galaxies. And that system holds pretty well, pretty true in the nearby universe. But once we start getting out more distant, it falls apart. Galaxies don't have the same structures. And so we want to learn about how that whole sequence formed in the present-day universe. We want to know how the heavy elements formed. And we want to know about the interactions of the galaxies with their surroundings. So we think the interplay between galaxies and the gas that maybe feeds galaxies and feeds star formation. And then the galaxy star formation and black holes, of course, give this outward winds. And so what is that interplay between galaxies and their surrounding environment? So all those questions we'll be able to learn more about those questions with Webb, because we'll have this new telescope in this new wavelength regime in order to study these processes in detail. So it's the very fundamental question of how we go from those tiny red blobs in the Hubble Ultra Deep Field to these gigantic galaxies that we see in the present-day universe that have these huge black holes at their centers. So we're able, of course, now with Hubble to study this in a statistical sense. I'm interested in galaxy mergers, and so this is a sequence, a snapshot of different galaxies that Hubble has taken. Of course, these processes take billions of years, so we have to study these things statistically. But I'm really interested in that process of how galaxies grow over time, and we think that this merging process is one of them. One of the really fun things about astronomy also is the interplay between theory and observations. So this video is showing steps between theory, simulations, which is what this part is, and then it will fade to an actual Hubble image. And so in this way, we're able to have theory inform observations, and then observations feed back into theory. But it's always a good thing when you're doing theoretical simulations, and then the observations match up. And the great thing about Hubble is we have this wealth of knowledge, this wealth of data that allows us to go back and do these studies. So this third big theme for Webb is to see stars and protoplanetary systems being born. So back to the iconic Eagle Nebula here. So some of the detailed questions here that we want to answer. So these protostellar clouds that host the baby stars and the baby planet systems, how do those collapse? That's sort of the beginning point of forming stellar systems, solar systems, stellar systems. But there's a lot we don't know, and theory plays into this, but there's a lot we don't know about how they collapse down to begin with, and how the hydrogen at the centers of these clouds actually form their stars. I mean, stars are the building blocks of galaxies, and star formation is a very fundamental process in the universe, but there's still a lot about that process that we don't know. And we also want to know, same thing as with galaxies, how does the environment in which stars form, how does that environment affect the star formation, and then vice versa, how does the star formation affect the surrounding environment? So similar to galaxies, that whole environment interplay with the formation of these objects. And then getting down to thinking about the planets that are forming, these baby planets enshrouded in dust. How do those protoplanetary systems form? How do the dust grains come together and form the planets to begin with? And again, this goes back to the fact that these systems are enshrouded in dust. So this is another image of, this is the Carina Nebula, a Hubble optical image. And here is the perfect example of where stars are born, inside these big dust clouds. And so here, the image will fade here from optical to infrared, and again, you can see the utility of infrared in this area of study because you're able to peer into that cloud, to see that newborn star through the dust, and to see its interactions even. In this particular case, you see the stars blowing jets, and so it's affecting its surrounding environment. So infrared is going to play a critical part in helping us answer questions about how early stars form and how protoplanetary systems form. And then this one. This is a fun one. So as I said, I study galaxy evolution. I'm really excited about what Webb will do in the area of galaxy evolution and finding those first galaxies. That's all going to be really, really cool stuff. This area is fairly far from my own personal area of research, but I think this is maybe the most exciting thing that Webb does, is to study exoplanets. And Webb will also have the capability to study planets within our own solar system. So everything from Mars on out, Webb will be able to study. And we have a very active planetary science team that is working on ways to use Webb to observe these objects in our solar system. So we fully plan to do that. So what do we want to learn? Of course, lots within our own solar system, but then in terms of exoplanets, what are the physical processes that lead to these planets? So sort of stepping from that last science theme of protoplanetary disks on further to when the actual planet formation happens. And then, of course, we want to be able to relate these exoplanet systems that we find elsewhere to our own solar system, and it will help us inform the studies of formation of our own solar system. And then, of course, habitable zones. How are they established? How do water and other elements get embedded in these habitable zones of exoplanet systems? So lots of really good questions there. Of course, we find exoplanets by transits. So the Hubble Space Telescope, of course, has been really instrumental in this in the last few years. And so this is a transit, and from just this very basic process of watching planets transit in front of their stars, we're able to learn fundamental things about the planets, like their relative masses and their distance and their orbital times. So there's fundamental things we can learn from watching planets transit their stars. And I think that one of the things that the Hubble Space Telescope has given us is really this knowledge that planets are common. So how many have seen this, the Ori, the Kepler Ori? A few of you out there, okay. So this, to me, is one of the best astronomy visualizations there are. So this shows, and this is several years old, so this is certainly not all the Kepler planets, but this gives a visualization of the variety of exoplanet systems that Kepler had found to date. It's much bigger now. But what you see here is that just the variety of planets, right? Who would have dreamed that planets would have been not only this common, but this wild, right? There are planets of all different sizes orbiting their different sized stars and, multiple planet systems. I mean, it's remarkable to me that when I was a kid, the only planets we knew of were in our own solar system. And now we know that planets are absolutely everywhere. The Milky Way is literally teeming with planets. Statistically, almost every star in the Milky Way likely has at least one planet. I mean, go outside at night, point up at a star, probably has a planet around it. That's a fundamental paradigm shift between when I was a kid and now. And I think that is really incredible, that Kepler has given us this knowledge, and Kepler's a relatively small telescope. It stares at one part of the sky, does one thing, but it really has given us this immense knowledge of planet systems, and really just the fact that planets are common, something that we didn't know. So the next step, of course, is to do spectroscopy of these transiting planets. So we want to go from knowing that the planets are there to knowing what they're like. And this is going to be one of the big jobs of the James Webb Space Telescope. Now, so what do I mean when I say transit spectroscopy? What I mean is we want to watch these planets orbit in front of their stars, watch the starlight pass through the atmosphere, and then from that starlight filtering through the atmosphere, learn about the chemical components of that atmosphere. Sounds pretty simple, right? It's relatively simple, theoretically, but technically, it's really, really hard. And this image shows why. So this is the Venus transit from a few years ago. This is a real NASA image from one of our solar observatories. And so what you see here, which is the common theme, is that stars are bright, planets are tiny and their atmospheres are minuscule. So separating out this signal from the bright stars and the tiny atmospheres is really technologically challenging, and we really couldn't do it in earnest really until now. So with Webb, we hope to be able to do that. We plan to do that. And every time I talk about exoplanet science with Webb, I always say, and I still say, that we have to get really, really, really lucky to find a system that might potentially have habitable planets. But sometimes nature delivers. And we had this awesome result last week. And of course, we don't know. We haven't studied these planets in detail yet. But how incredible that we have this planet system 40 light years away. This is our backyard. And it's the perfect system. It's a little tiny, faint star with a bunch of planets, 3 of which are solidly in the habitable zone. And so absolutely, this is going to be a great target for the Webb telescope. Who knows if the planets have atmospheres? A lot of planets, systems like this, planets close into their star, they can be tidally locked so that one side of the planet faces the star the whole time it's orbiting. We don't know. What we know is that those planets are there, and we definitely intend to look at them with Webb. So again, 7 planets orbiting this nearby star. Just sort of hit the jackpot. I mean, what an incredible discovery. And so I can't imagine that my exoplanet scientist friends aren't drooling over this discovery and waiting for Webb. These planets were first discovered by the TRAPPIST telescopes in Lucia. And it's also a great story of how the ground-based telescopes, and this is Spitzer in this case, this result last week was from the small infrared Spitzer telescope. So a great story of how ground-based telescopes and space telescopes can play together to get these great results. But we really, really do need Webb in order to do spectroscopy for these faint, small, rocky planets. So that TRAPPIST system, a lot of fun. Really excited about that. So those are the science themes, the 4 broad themes with all these sub-questions and all this great stuff that we hope to be able to find out from the James Webb Space Telescope. So the great news, of course, is that we're building it. And not only are we building it, but we have built it. So almost all of the hardware for the James Webb Space Telescope, practically all of it, is finished. It's built. And a lot of the pieces have been built for years. This is a project that's been going on for decades, literally now. So the James Webb Space Telescope was first conceived shortly after Hubble was launched. So us astronomers, we always like bigger telescopes. And so shortly after Hubble was launched, we started thinking about what might be next. And I say we, I was in elementary school, so I was a part of that conversation. But astronomers started thinking about that. And cool thing about the astronomy community and other science communities as well in the US, every 10 years, astronomers from around the world really get together and they say, what are our biggest astronomy questions today? And what do we need to build to answer them? And so those are the decadal surveys. And in the 2000 decadal survey, the answer to what do we need was the James Webb Space Telescope. So 2000 was really when it started getting going. There was development work, R&D that was done before that, but 2000 was when it got its seal of approval to start to move forward as a NASA mission. So that was a long time ago. It turns out building something like this is really hard. No surprise, right? So I want to take you through some of the steps of building it and some of the pieces. So of course, the iconic part of the telescope is that gigantic mirror with hexagons, these hexagonal segments. The mirrors themselves are made out of beryllium, and they have a really thin coating of gold. So the Spitzer telescope also has a beryllium mirror. It turns out that beryllium is a really good material to put out into deep space where it's very cold. It's very strong and lightweight, and it doesn't change shape much under drastic temperature changes. So obviously we have to build the telescope on Earth. In space, it's very cold, and so we need a material, all the materials need to be able to withstand those extreme temperature differences. So the mirrors were individually manufactured and tested. This is an image of the 3 of the 18 mirror segments coming into NASA Goddard. This all happened within the last couple years. So the mirrors were one of the technology elements on the telescope that really took a lot of lead time. Making these mirrors was really, really difficult. So in addition to the fact that just working with beryllium is difficult, the telescope itself has to be very, very precise in its prescription or its shape. And so if you imagine the Webb telescope mirror, so it's 6.5 meters across. So imagine stretching that whole mirror out to be the size of the United States, right, coast to coast. The biggest bump on that mirror would be a couple inches. So that's how smooth the mirror is. So machining these mirrors and coating and polishing them to that incredible precision is really difficult. So we started working on the mirrors really early on in the mission. And as of last year, a couple of years ago, we had them all completed, all individually tested. And then everything on this telescope has a practice round. So this is an image of our specially made robotic arm installing one of the test mirrors on a test structure. And this happened at Goddard back a few years ago. And then about this time last year, it's been almost exactly a year ago, we finished installing all of the 18 primary mirror segments onto the backplane. So this process took several months, of course, after all those individual tests of the individual mirrors. And of course, the process of placing them, and then they had to be individually mounted. And as you see, they're not gold here. So they all have these black caps on them to protect them while the mirrors were being installed. And so this whole process, again, was completed about a year ago. And then we took the caps off, and we have this beautiful gold mirror that was able to be seen at Goddard for a short period of time. It's now in testing, which I'll talk a little bit more about later. So in addition to the mirrors, of course, a really important part of the telescope are the instruments. And as a scientist, of course, the instruments are really important to me. This is where the data comes from. This is where the images and the spectra will come from. So we have 4 instruments on the Webb telescope. We have a near-infrared camera. We had a mid-infrared instrument. We have a near-infrared spectrograph, which has some really cool spectrograph technology. And then we have what's called the fine guidance sensor and the near-infrared imager and slitless spectrometer. That's a mouthful, but I wanted to say it because that is a Canadian instrument. The Canadian Space Agency is supplying the fine guidance sensor and the NIRISS instrument. So those two are packaged, those are functionally different, but packaged together as one, and they're provided by Canada. The fine guidance sensor is a mission-critical instrument on the telescope. So it essentially provides guidance and stability for the telescope when it's pointing at the objects it needs to observe. And then the near-infrared imager and slitless spectrometer will be able to take spectra of galaxies and of planets. It will be able to do actually really important exoplanet science. And so this particular instrument will be, I think, really instrumental to all 4 of the science themes that we have for Webb. So really excited about all these different instruments. All 4 of these instruments have now been integrated onto the core package together that goes on the back of the mirror, of the big gold mirror. And so here is a picture of part of that integration process. Now, all of these instruments, just like everything else on the telescope, were tested at an instrument level, at a subsystem level. And then when they're put together into these pieces, they are tested at a higher level. So all the instruments have been through 3 rounds of cryogenic testing. They've also been through vibration testing, acoustics testing, all of those sorts of things. So the instrument's really important. The sun shield. So we just finished completion of the last sun shield layer in the last year. So this is the sun shield is made out of a material called Kapton. It's a very thin plastic material with a highly reflective coating. It's 5 layers And as you can see, there's a person up there for scale. It's really big. Everything about this telescope is really big. So the purpose of the 5 layers is so we can get very, very cold on the top. So in this sort of configuration, the mirrors and instruments would be up on top, and then the spacecraft buses down on the bottom. And so in that configuration, of course, the telescope would always point out away from the sun. So the sun shield is exactly what it sounds like. It shields the mirrors and instruments from the sun. And the reason for the layers is for thermal dissipation. Okay, so the temperature difference between the bottom layer and the top layer is about 600 degrees. So it turns out space is really good at that sort of thing. And so we're able to get this extreme temperature difference. Now, that poses a lot of issues too. Nothing about this telescope is easy. So the thermal properties of this telescope, of what goes on, even in the center section where you have the connection between the mirrors and the spacecraft underneath, lots of really interesting thermal physics problems that we have to solve in order to make this telescope work. So that's the sun shield. As I said, all 5 layers are completed. This is a video of some deployment testing. So Northrop Grumman is our prime contractor, and this is at their facility out in California. And so all the layers, of course, have been under cryogenic testing. This is a deployment test, obviously a manual deployment test. Lots of really, really extensive tests that go on for this telescope. As I mentioned, it's going to be far away, 4 times further away than the moon, 4 times further away than human beings have ever been. We cannot service this telescope like we serviced Hubble. So the telescope isn't serviceable. One of the reasons we have such a long, extensive test program, this telescope has to work once it gets into space. We can't go and fix it. And so that's why we have such an extensive test program here. The logistics for this telescope amaze me. So the engineering and the science obviously are amazing, but carting around pieces of a telescope that are this big, not an easy logistics problem. There's whole teams at NASA that work on logistics. So this is inside the white box is the big backplane structure when it arrived to NASA Goddard back a couple of years ago, and it's carted around on a C-53, that's the U.S. military's largest military aircraft. And this landed at Andrews Air Force Base outside of D.C. They shut down the Washington, D.C. Beltway in the middle of the night and trucked the backplane in this truck along the Beltway at 5 miles an hour. It was really just interesting logistics for the whole telescope. And then, as I've mentioned, the test program for this telescope is extremely extensive. This is our cryo vacuum chamber at Goddard. So this is one of the tests that we did on the instrument package. And so again, we test the structure, and then we test the instruments integrated into the structure. And the instruments have all gone through 3 cryogenic tests. So that's testing the instruments down to about 10 degrees Kelvin, or 10 degrees above absolute zero, 10 Kelvin. So space is very cold, so we have to test all of our components in cryogenic temperatures. Now, the cryo vacuum chamber at Goddard was not able, it's a typical nitrogen cryo chamber, wasn't able to get that cold, so we had to use helium. So we installed a huge helium shroud inside the chamber to get us down to the cold temperatures that we needed to test these elements of the telescope. And so this is one of those tests. So that huge cryo chamber there, the top sort of is moved by a crane, lifts off, and then we've undergone these extensive tests of the instruments. The tests of the mirrors will happen, the individual tests have already happened, but coming up later in the program, we will send the whole telescope element, so the telescope and the instruments together, down to the Johnson Space Center in Houston to undergo full end-to-end optics cryogenic tests. It's a really critical test that's coming up later on this year. This happened just a couple of months ago, actually. So this is after some of the tests we had in the clean room at Goddard. We installed this huge tent over the telescope. So this, you can see now the mirrors, the two wings are folded back, the secondary mirror is folded up, and then the instruments are installed on the back of the mirror. So we installed this tent over the mirror because we had to move it out of the clean room to go to our other testing facilities outside. So everything is assembled inside the clean room. That's why everyone's in the protective bunny suits. But our vibration facility and acoustics test facility are in different parts of the building. They're just different facilities. And so we had to build all this test equipment in order to take the telescope, move the telescope from place to place. And so this is installation of that huge tent to go over the telescope here. So this is after the telescope and the tent has been moved out. And this was installation onto the vibration table. So the telescope is launching into space. It's launching on an Ariane 5 rocket, which is a European Space Agency rocket. And of course, the rocket ride is bumpy. So we have to shake the telescope to make sure that it will withstand the stresses that it experiences during launch. And so we had these custom vibration tables built for the telescope. Turns out there weren't any big enough in the world to accommodate this telescope, which is a common theme. And so we completed these vibration tests just about a week ago. So this is a very recent occurrence in the life of the testing of this telescope. So this just happened very recently. Now, when you test things, occasionally you find problems. So in one of the first tests we had a little bit of a high load on one of the accelerometers. So we had to pause the test, make sure everything was okay, which it was, and then continue. But that's the exact reason we test. We have to make sure this telescope works once it gets into space, and so that's why we test on the ground. So this is an image from about 2 days ago. So this is like hot off the presses. So after we finished the vibration test, we moved the telescope into our acoustics testing chamber. So imagine enormous speakers that are going to blast the telescope with sound, and of course this is to test different vibrational frequencies of the telescope. So that test started just a few days ago, and it should be finishing up any day now. So lots of really critical environmental tests that are going on right now. So the telescope is big, that's a theme, right? It's too big to fit inside the rocket, fully deployed, so we have to fold it up, and it deploys once it's in space. So this is the deployment sequence of the telescope. So the first thing that pops out there is the solar panels. We'll use the solar panels for power, of course. The antenna pops out so we can talk to the telescope. And then as the sequence goes on, you will see that 5-layer sun shield slowly unfolds. This whole process starts fairly soon after launch, and then it lasts about 14 days. So how many of you saw the Mars Curiosity 7 Minutes of Terror? It's a great video. Go check it out if you haven't seen it. So they had 7 minutes of terror. We have 2 weeks of. So again, one of the reasons we test this telescope so much is because this is hard. Okay, make no mistake about it. This is really, really difficult. This is coming up to the edge of impossible engineering. And so we're doing it at NASA, though, and that's one of the most amazing things about NASA is I think that we're able to take on these huge challenges and we're able to do them. And so this whole deployment process, again, takes about 2 weeks. And then after that all happens, we'll have a commissioning period where we take a few months to slowly phase up the mirrors to make sure the mirrors are all perfectly in shape. We'll turn on the instruments one by one and sort of bring those up to working order. And then we'll get the first science images sometime in the first 6 months, and then routine science operations will start about 6 months after launch. So you can expect to see the first images from the James Webb Space Telescope in sort of early 2019. What will they be? We don't know yet. We're undergoing a process now to figure out what those first observations will be. And in fact, we just had a huge science milestone this week. A lot of our milestones we've been talking about lately at NASA have been engineering milestones. We got through this test and we got this thing built, and all these different engineering milestones have been met. We've met a scientific milestone recently this year as the call for proposals came out. So the call to ask scientists to write proposals to use this telescope came out, and the letters, the notice of intent that you're going to propose are due on Friday for the early release science. So it's real now. It's really real. It's really happening. We launch next year. That's soon. So October of next year is when late next year in 2018 is when we plan to launch. So the James Webb Space Telescope is the project I work on and the one that I'm probably most excited about, as you can probably tell. But at NASA, we have a whole huge suite of astrophysics missions that we are currently operating and that we will operate in the future. And so this is just a suite of the missions that we're involved with here. We have one, the NICER telescope is expected to launch in April. So that's going to launch on a SpaceX rocket, and it will be installed on the International Space Station. So we have lots of fun collaborations with the human spaceflight side of NASA, where we install spacecraft on the space station. So we have a whole fleet of astronomy observatories, astrophysics observatories at NASA. Of course, the ones that come along like Webb are the big ones, right? Most of these telescopes are relatively small telescopes that are focused on one specific thing. So the Kepler telescope, for example, was, its mission was to look at this one part of the sky, look at exoplanets. That's what it did. So most of NASA's astrophysics missions are like that. They have one sort of mission, one goal. And then you have the missions like Hubble and Webb that have these sort of multi-purpose missions. So they're built to explore a wide range of science questions. And I want to give a particular shout out to the next big mission after Webb, which is the WFIRST mission, the Wide Field Infrared Survey Telescope. So while Webb and Hubble are similar in that they look at sort of small pieces of the sky deeply, the WFIRST telescope is going to take images of a wide swath of the sky. And the WFIRST mission, if you haven't heard about it yet, go check it out, learn a little bit more about it because I'm running out of time. But its two primary science themes are, get this, so cool, exoplanet science and dark energy, two of the most fun things that we have. And so really excited about this mission, scheduled to launch in the mid-2020s. So excited about WFIRST, really excited about Webb. I invite you all to go online, go to our website down here in the bottom left corner. Follow us on social media. Join us in this journey leading up to launch, marching to launch next year. And of course, then to the science that we'll reveal soon after that. This journey for me has been personally just really exciting to be a part of a team that's working on something that's so significant. This telescope has already shattered boundaries of space technology. But as a scientist, of course, I'm excited about the science that we'll do. And I've told you a little bit about the core science themes, the core science questions that we hope to answer with this telescope. And I'm sure we'll answer those. That's going to be a lot of fun trying to answer those. But for me as a scientist, I think the most exciting thing about these big, bold missions are the answers to the questions that we haven't even thought to ask yet. In the end, these missions that we build are all about the promise of discovery. They're about the promise of hundreds of billions of stars in these hundreds of billions of galaxies and untold surprises just waiting to be discovered. Thank you.
right, well, let's open the floor to questions. Aiden, you're on.
So how do you protect the sensors before the sun shield has fully deployed?
That's a really good question. So the whole process of launch, of getting out there, is a process where we have to make sure that the rocket is sort of pointed in the right way, and then when the rocket cone falls off, we have to make sure that it's pointed in the right way. So it's all about making sure that the spacecraft is sort of pointed in the right direction. So if you notice when it starts off, the sun shield is sort of wrapped up around it. And so when it starts to unfold, to deploy, that's when we have to make sure that it's pointed in the right way, essentially. But that's a great question.
And what about the thermal aspects of it? Won't have a lot of problems relating to that?
Yeah, so the thermal aspects of the telescope have been one of the most challenging things. And even just the thermal properties from sort of the cold side under the sun shield to the hot side under the sun shield to the cold side on top. So the sun shield does a great job of protecting the mirrors and instruments. But there's that middle section, right, where the telescope basically connects to the spacecraft. And so figuring out the thermal properties of that section has been a real challenge. But we think we figured it out, and we expect that it's going to work like we want it to. Yeah.
Thank you, Aiden. All right, let's go online as others line up. Here's a question tied to the length of the mission. What is it like to work on a project that is decades in the making?
Yeah, so I've been involved personally in this project a little bit since I was a graduate student. My dissertation advisor in grad school is one of the 10 interdisciplinary scientists on the mission, and so I got interested and involved early on as a grad student. But you're absolutely right that these missions that span decades, people spend their entire careers on these missions sometimes. And so there's certainly people that besides me, that have spent a lot longer than I have. And so I think it's great to be a part of that. Part of that is just the team that comes along with it, being a part of such a big team that's designing something like this and building something like this. But at the same time, we have to launch this thing to space. I mean, I already can sense some of the team at Goddard. The telescope itself will leave Goddard in April, sometime, next month. And there's a little bit of sadness, like our telescope is leaving. And then someday our telescope is launching to space. It's like sending a kid off to college or something. But so there's all parts of that. It's funny because it's an emotional thing. Like you pour your life into these missions, especially these missions that span decades. But it's a fun thing.
In theater.
Okay, so from my understanding of this, you're going to have to send an initiation signal to the satellite or the telescope to get it to unfold. Is there any redundancies you've built in so that you can, and how are you actually going to communicate to the satellite to make sure that it gets the signal?
So the operations for the Webb telescope will be run out of the Space Telescope Science Institute in Baltimore, Maryland, same place where the Hubble is operated. So we use Ka band, normal sort of communication with the satellite, and absolutely there are redundancies built into the system. Not every move, you saw the deployment. Not every movement has redundancy built in. It's just impossible. But many of them do. And the ones where we can place redundancies, we do. And so the process of communicating with the telescope, like you said, sort of happens one by one. And in fact, later this year, we start a full-up dress rehearsal of sorts of the launch and of the commissioning because it takes so long. And so, there's going to be 24-hour shifts and there are going to be people working. And so rehearsing all this and rehearsing what happens if something goes wrong, what do you do? So there's a whole rehearsal process for the whole process.
I'll take another one from the online list right now. The question is, was it just lucky that the TRAPPIST planets are on the same orbital plane as the solar system, or is that common?
So it, lucky is an okay word to use, sure. So yeah, in a sense it is luck. It's statistics really, but you can say it's luck. So yeah, some of the systems that we see in the sky will just have the right inclination that we'll be able to see them transiting. Of course, a large fraction of the exoplanets won't have that. You know, if they're face on, we can't see the transits. We can observe planets that are there in other ways, radial velocities, those sorts of things. But yeah, it was luck. I guess it was luck. You could say that that the TRAPPIST system happened to be sort of edge on.
Thank you. In theater.
So you mentioned that W first is going to be used to study dark energy. How do you study dark energy?
What a great question. Yeah. So. Yeah, good question. So what it's going to do is it's basically going to survey many galaxies and go into the detailed distances of the galaxies, and from that just try to sort of hone in on the parameters of dark energy. So dark energy, of course, well, it's this. When astronomers don't know what something is, they call it dark, right? We got dark matter, we have dark energy, and it makes up most of the energy mass content of the universe. In fact, yeah, so everything I've talked about tonight, the billions of stars and planets and galaxies and all that makes up 5% of the universe. The rest, the 95%, we have no idea what it is. Dark energy, dark matter, don't know what it is. But the W1 telescope is going to do this really cool technique that you should go online and read about. Go on our website. It's called baryon acoustic oscillations. So it's basically studying sort of the details of how galaxies affect their surroundings. And then also we'll be able to do some sort of similar work that Hubble has done, for example, in honing in on those parameters of dark energy by studying the distances to galaxies precisely. So it's all about precision. And with W1, for these particular studies, it's all about volume. So you need lots and lots of galaxies to be able to hone in on some of these problems. And that's why we're building W1 the way we are. It has this huge area, huge field of view.
Thank you.
Let's take another in-theater question.
I'm not sure what my question is. So you mentioned earlier about looking through a straw and you would see 10,000 galaxies through the straw. How do you map the 5% of the universe that we can see? Who's the cartographer who's mapping what we can see? Do you have a space compass that you use that you move 2 degrees at a time? It's such a big challenge. I don't know how you map the universe.
Yeah, that's a great question. And so how do you map the universe? There's, the sort of pencil beam surveys I talked about, the looking through a straw, that is more to look deep into space. So we can actually map the cartography of the universe, if you will, more efficiently with large area surveys. So for example, the Sloan Digital Sky Survey on the ground, the Sloan telescopes, have been able to sort of map where the galaxies are. And this is how we found out about things like large-scale structures. The galaxies aren't random, that if you look at millions of galaxies, that you see that they form this cosmic web. And so that is a lot of the job of a lot of ground-based telescopes, and W1 would also have a part in that as well.
I'm going to go online again. I think I have 2 that are similar. So the one question is, why isn't the mirror in a protective housing like the Hubble was? And I think ties to this question, what happens if something hits the telescope, and how would you prevent it from happening?
Yeah, okay. So I'll answer the second one first. We can't prevent things from hitting the telescope. So we have a fairly good idea about that part of space, the L2 part of space, because we have spacecraft out there. We have a fairly good sense of what the micrometeorite environment is out there. So we know we'll get hit by little micrometeoroids. So they'll come along, they'll poke us, poke a hole through the sun shield, no big deal. We'll get little pocks on the mirrors, no big deal. So we expect for it to happen, and we don't expect that it will be a problem. Now, if something like boulder size comes along as it smacks us, we're in big trouble. That's a bad day. But statistically, that's really, really unlikely. We don't expect that to happen. So we expect to get hit by little pieces of space dust, and it won't be a big deal. And then the first question was, why why doesn't Webb have a mirror? Basically, why does Webb look weird, right? So when you think of a telescope, you think of a mirror with a tube around it, right? That's what backyard telescopes look like. That's what the Hubble telescope looks like. It's literally a mirror with a big tube. And the reason for that, of course, is to protect the mirrors, the detectors, whatever you have, from ambient light, from outside light. Webb is different because it's an infrared telescope, and so what we really need to protect the mirrors and instruments from is infrared light. And your big infrared source in that part of space is the sun, which is why we have the sun shield. So in effect, you can sort of think of the sun shield like the tube of a telescope, except it's just formatted in a different way.
Very good. In theater.
Can you tell me how big the package is that's actually going on the spacecraft, on the launch vehicle, how much the package weighs, and how much did the entire telescope cost?
Sure. So, so the easy ones first. The whole telescope, top to bottom, is sort of 3.5 stories tall. So you could sort of get a sense from the full-scale model picture that I showed you, and from end to end on the sun shield, about the size of a tennis court. So that's the size, and that's of course why it has to be folded up so small. The inside of the rocket fairing that we're fitting in is about 5 meters, so it has to be all packed up to be no wider than about 5 meters. Mass. I don't know the mass. I should probably be able to rattle that off, but I don't know that off the top of my head. It's scientist to me, I'm not an engineer. But I do know this, fun fact, is that Webb is about half the mass of Hubble. So it's this big, huge, enormous thing, but it's relatively sort of fragile, lightweight. And of course, that's because we're going into space. We need to make things as lightweight as we can. And also because there's a weight limit for the rocket. If you make the telescope as lightweight as it can be, then you can use your extra mass margin to pack in fuel. And so the more fuel we have, the longer we can operate the telescope. So the life-limiting factor for the telescope is propellant. Out in that part of space in L2, we sort of have a big lazy orbit around that theoretical L2 point. And so it takes rocket fuel to sort of keep it in that orbit a little bit. Cost. So the telescope cost to launch is $8 billion, billion with a B, and so that's the last couple of decades of work. So that's from the beginning up through launch. That's a lot, relatively speaking. That's a lot for a NASA mission. This is one of NASA's strategic big missions. Again, all most of the other telescopes I showed you on that chart are much smaller and focused. So that's why they only come around as often as they do, not quite so often. We launch these other smaller telescopes into space, every several years, whatever. But in the end, it will be less expensive than Hubble. The Hubble, especially if you count the servicing missions, will in the end have been more expensive. And so the subtext, the sub-question there, of course, is the obvious one: is it worth it? And I think that's something that we as a society have to decide, right? These are taxpayer dollars. This is a government-funded telescope. And so we as a society have to decide if we want to invest in that. And I think for NASA, when this question comes up, over and over, the public has been enthusiastically behind these endeavors. And in fact, if you poll the public and ask them what they think the NASA budget is, they way overestimate it, about 20 times, 40 times. And so the question of is it worth it is an important one that we have to discuss as a society. Of course, I think it's worth it because I'm a scientist. But I think that if you ask these deep questions, that I think society tells us that it's worth it too.
I'm going to jump back to an online question before going up to the microphone. The question is, will the James Webb be able to confirm the idea that black holes are critical to galaxy formation?
Ooh, that's a great question. So I think yes. I think that Webb will absolutely make large strides on the whole area of how galaxies and black holes evolve over time, and of how black holes interact with their galaxies and vice versa. So we know that black holes are common. These supermassive black holes with billions of times the mass of the sun exist inside every galaxy that we know of, every nearby galaxy. How they got that big is a big mystery. No idea. We think this galaxy merging process is a really important part of that process, that maybe the black holes merge. Or who knows, maybe the galaxies collide together and the black holes get kicked out. You know, there's a lot that we don't know about that process. But again, that's one of the reasons we build these big telescopes, is to help us learn more about that process. But I think absolutely Webb will help us learn more about the whole process of how black holes form over time, how they interact with their galaxies, and how the galaxies influence the black holes.
Let's go in theater.
The question is about sequence of time. You mentioned that the intention is to look deeper in the universe in order to see back in time. The question, how do you know that further is further in time? We know that it takes time for light to travel.
Right.
We know that universe expands. We know that there are all kinds of processes of forming stars. So is it necessarily true that further is further in time?
So this whole idea of looking further in distance, the idea that translates to looking back further in time, really does rely on the assumption that light has a finite travel speed, and that we can sort of map it back, right? And so the process of how we use the light from galaxies to figure out the distances comes through mostly spectroscopy. So we take spectra, the signature or the chemical fingerprints of galaxies, and we look for specific emission lines. And we say, there's a hydrogen line. I know if I look at hydrogen here on Earth, this is the wavelength where it happens. And so if we look at a galaxy and we say, that line's been shifted to the red part of the spectrum, we can calculate then how far away that galaxy is. So that's the process by which we determine the redshifts and the distances of galaxies. But it does fundamentally rely on this fact that light has a finite travel speed.
I think there's one more question here in the theater. Perfect.
I've got two questions. One's easy. Who's James Webb? And
Okay.
the second question is, I've been to a couple lectures where they talk about the universe. I'd like to hear what you think, what is beyond that universe. Is it finite, or do you think it goes forever?
Okay. So like I said, first question's easy. Second question, not so much. So the first, James Webb, I was the leader of NASA, the NASA administrator, during the development of the Apollo program. So he was largely responsible for the conversations with JFK, with Kennedy, that eventually got humans to the moon in Apollo. But in addition to that, he did something very instrumental that changed the purpose of NASA in the very, very early days of NASA. He said that in addition to launching rockets to space, launching people to space, that NASA should be doing science. So James Webb really instilled the value of science in NASA early on. And so that was the reason this telescope was named after him. Second question. Wow, yeah, that one's a lot harder. So you ask what's beyond the visible universe, basically. So as a strict observationalist, I will say we can't observe it, so we don't know. But going beyond that, we don't know. I'm really interested, and I've talked to a couple of people here today about the prospect of what lies beyond our observable universe, about the prospect of multiple universes, the multiverse, about the idea that we could live in sort of a bouncing universe. Now we know that the universe is not only expanding, but that it's accelerating in its expansion. So that's what dark energy is. We don't know why, so we call it dark energy. So we don't expect that since it's accelerating, that it would stop and slow down and come back and bounce. But there could be scenarios in which instead of bouncing sort of back and forth like that, what's the right word? It's not bounce, but basically that other universes could sort of be born. Multiverse is not my area of expertise. But it's super interesting. And so I think that's one of the cool things about this place, actually, is there's all these sort of big questions about theoretical physics and about string theory and about the multiverse. It's really fun stuff. But for now, I'm interested in what Webb's going to see. And we'll be able to see back to the early universe, which is going to, I believe, reveal really a lot about the whole evolution of our universe. I mean, we're missing the first step, right? We've done all this study of all these galaxies looking back to the most distant ones we can, but we're really missing the first piece of the puzzle and how the galaxies got started. And so I think that's going to be one of the really cool things that Webb does is to help us learn more about that very first epoch of galaxy formation.
Ladies and gentlemen, Dr. Amber Straughn.